All right. So I'm going to talk about NIF debugging. The first thing that I wanted to say was just, if you're not sure, if you don't already maintain any NIFs, if you don't have any NIFs already, kind of you can, and you're just wondering, should I write NIFs? I mean, you can skip this talk basically, because I'll tell you right now, you should avoid writing NIFs. It should be, as a matter of last resort that you actually write a NIF. Yeah, so if that's all you needed to know, then go watch Scott Fritchie's talk instead, because it's probably going to be awesome. But otherwise, I'm going to assume that you have NIFs in your system that you have to maintain. Right now, I've got, I guess, about a dozen that we use in production that I have to keep track of, and so I'm going to talk a bit about where those come from. Go ahead. And you
just said to avoid NIFs. How do you do crypto?
Crypto is a great example, and I'll talk about it. And I was going to say, since we're so few, feel free to interject and feel free to comment, because there's not really much point in not asking questions right away. There's enough people that. Like crypto is one of the classic cases. It's like where do you end up? Why do you end up writing a NIF, right? So your first period with Erlang is just awesome. You go through that honeymoon period where everything is great and performance is great for some things, right? And then you hit a wall where suddenly you need to do something highly computational, or a variety of things, but usually some serious number crunching, and Erlang is just way too slow. And so, about crypto specifically, let me talk just about what usually happens. I think I've seen the archetypical arc here is that programmers come from, especially you come from a background of speeding up languages like any of Ruby, Python, Perl, even Java before Hotspot. Basically the rule of thumb was you reach for the foreign function interface or write an extension. And so that's just the natural habit. So I think that when people come to Erlang, there's a tendency to, when you see a performance problem, jump straight to implementing a NIF, because clearly that's the FFI and that's the logical thing to do. But in fact, that's not so. And there are a few exceptions. In the case of crypto, what's a better way? You have a number of other ways of interacting with external code in Erlang. I think the most Erlang-y way is actually as another service. If you can actually abstract that code out into a service that you talk to through some network or interprocess mechanism, that's the really early Erlang-y way to do that kind of thing, and plays really nicely with the whole system. The next closest analog to that is ports, right? Which are basically where you run a program that's sort of supervised by Erlang, and you speak to it through standard in and standard out. And obviously one of the problems with that is that you basically have to serialize everything that you're communicating back and forth. So there are a couple of cases, particularly anywhere where you have to work with a large volume of data, or the case of crypto is just interesting just because usually you want to minimize the ways in which you're transmitting secret data and things like that. So these are things that often end up being done as NIFs, and you may not have an alternative to writing them as a NIF.
It is 80% of our CPUs. So.
Yeah. Well, for sure, right? And crypto is always a big thing, especially because you often want to take advantage of specific CPU-specific optimizations and things like that. And obviously, there's so many orders of magnitude between trying to implement that in Erlang, or even as a port, where you'd have to transfer everything that you were encrypting or decrypting to the port and back again. So I should mention port drivers, right? Where before there were NIFs, you could link a port into the VM process. You still had to communicate, but you basically you had a much tighter communication mechanism. But of course, that actually was the worst of both worlds, because now your port driver code can crash the VM, but you still have this isolation in how you speak to it. So from that point of view, the NIF API seems like a much better way to do that sort of thing. So I mean, things that I'm going to point out, it's like NIFs very easily take down the VM in a really bad ways, right? This is where you don't let it crash. They can have memory leaks that are quite difficult to track down. Just measuring their performance is difficult, and specifically, I think it's well known, but their impact on the scheduler is really significant, and I think underestimated by people who start to write NIFs. As long as your NIF performance is really, really predictable, it's one thing. But as soon as you get into, especially crypto is a good example, because you may be calling out to the NIF for a long time, and basically you have a lot of really hacky mechanisms to try and make that work well with the scheduler. The least hacky of which is the dirty schedulers most recently. But even then, there are a lot of caveats to do with dirty schedulers. So and even then, just writing the NIF to actually use dirty schedulers properly is significantly more work than sort of the default NIF implementation that you would do kind of naively. And there's almost no way to win there right now. In terms of scheduling problems, it's very difficult to estimate what you have calls to sort of consume time slices, but it's extremely inaccurate, and in practice seems to have a lot of really bad impacts on scheduling in the VM. So I think that's something to really strongly consider. Everyone seems to find NIFs perform really well in the small, but as soon as you start using them in the large, where you've got a lot of processes and a lot of scheduling happening, performance is much more erratic, right? And I mean, we've seen all kinds of weird behavior. So I think that these are all things to bear in mind, and they're one of the reasons why, in general, now that I've inherited all these NIFs in this code base, I'm really against NIFs. I really feel like it really should be the method of last resort. It's definitely not. It's not a free speed win. Let's put it that way. So let's imagine that you do have NIFs, and basically everyone, one way or another, has NIFs. We'll talk about sort of what can you do. I'm going to look at three different, throughout this, I'm going to be talking about three different use cases. You have validating correctness, just, is this NIF actually behaving correctly? There's debugging, where you actually have something is actually going wrong with the NIF, is taking the VM down, and how do you debug that? And then there's benchmarking and improving performance, because that can be a really tricky thing. I'm going to describe some tools that I've built, but first I'm going to describe the tools that are already out there. One last note about when to write NIFs. So the other seduction of NIFs is you think, oh, a NIF is just a BIF, right? So NIF stands for native implemented function, BIF stands for built-in function. People often want the same benefit of built-in function from a NIF, and they think they're able to achieve that. But in fact, the NIF API is quite different from what a BIF has access to in the VM. And just as an example, you look at Jiffy has to call a dozen functions from the NIF API to do something that a BIF that does the same thing, like checking the type of a term, only has to mask 2 bits out of a term and do a switch statement. So there's actually quite a disparity between what you can actually do in a NIF versus what BIFs are capable of. So it's also something where if something is really of performance importance, it might not be too extreme to actually consider, I don't know, begging the OTP maintainers to implement it or submitting it as a PR as a BIF, because they are quite different, right? So we should avoid the illusion that that NIFs are basically just user-provided BIFs. Yeah, I love this quote from Richard O'Keefe recently, you know, and I think that kind of sums it up. NIFs violate Erlang. They violate everything that you wanted to have in your VM, and especially they make it really hard to. They mess with scheduling. They mess with reliability and robustness. So, you know, so then you try to. And a note about, well, you try to debug these things. And so first I'll show some things that go wrong. A note about pronunciation. So pedants will note that this is, I'm going to say Valgrind, but the correct pronunciation is actually Valgrind, because it's from Norse mythology, but just as a habit, I'm going to say Valgrind, so I apologize. Go ahead.
I just have to say this, we have a totally different experience. We use NIFs because we have to decrypt every packet it comes for.
Mm-hmm.
They run in less than 50 milliseconds. We never had a single problem with them. Our performance is, you know, we're doing 100,000%.
Did you say milliseconds?
Yeah.
Yeah, I mean, so my latency window is like 10 milliseconds. That's, I can't be doing stuff like that. I think if your NIFs are running for more than 1 milliseconds, you're really going to screw up scheduling.
No.
That's my experience. But
No, I was saying,
yeah.
I mean, we
Yeah.
use it every day.
Mhm.
Doesn't
No, it's good to hear.
have zero problems, so kind of
It's good to hear different things, but like, are you actually measuring sort of how that's affecting the scheduling?
So we profile it. I mean, we know exactly what it does. So
Right.
we've never had problems, so it's kind of.
Well, fair enough. Then, you know, all the better, right? And good luck to you. So, for example, one thing that you may want to do if you have NIFs that are crashing or leaking memory is you want to Valgrind them. But okay, first, usually before you discover what tools are there, you usually try the naive things like trying to Valgrind the VM itself. Yeah, it just, you can see here, so running the test suite took, you know, less than a second normally, but under Valgrind, first of all, it didn't report anything useful. It was filled with error messages, which I didn't reproduce here, and it took, you know, forever. So that, you know, that doesn't work. And other bad things. So one thing about like NIFs, if your NIFs allocate a lot of binaries, turns out that some of the binary allocation stuff calls out to the libc allocator, which has really bad contention in the case where you're doing a lot of allocation across many threads across many cores, right? So you might try to drop in different allocators, and luckily JE-malloc does happen to work, which is great, but you try to preload TC-malloc and you just get a segfault. And so there's a bunch of things that are iffy about trying to work with the stock VM. But so there are debug builds of the runtime system. And this is a really handy thing. I think this was like, I mean, if you've been maintaining and debugging NIFs for a while, you're probably quite familiar with this, but this, just finding out about this, because it's not extremely well documented, I feel, was a boon to me. You know, you can actually, you have to go into the ERTS emulator directory of OTP, and then you make type equals whatever, and then your flavor, which can be SMP or normal, I think. Anyway, and you get special builds of the beam, and you have to use this CRL script to invoke them. It has a ton of different options. It's really worth looking at all of the different options. Some of them are quite confusing. For example, minus GDB is what you would think would invoke GDB, but actually it invokes Emacs, which is surprising at first. It invokes GDB inside of Emacs. RGDB just runs GDB. And so that's like the debug build. There's a Valgrind build, which makes the runtime Valgrindable. There's the lock counter, LCNT, which I'll talk about in a bit. And you can build the whole system with the configure option with dynamic trace equals system tap, for example. And enables a lot of system tap probes, which is very useful for some kinds of introspection. I'll talk a bit about that, although so far I've not found it that useful compared to other approaches. So the lock counter is really handy. In this case, this allowed me to determine that locks were not a problem for this code. You can see there's like almost no collisions over hundreds of thousands of runs. This is like a good example of bad lock count output, where we have like 44% collisions on the process table lock, and it's a bad scene. And so that's actually really useful. That's extremely useful for sort of diagnosing some performance problems. But well, I'll talk about the caveats of it in a second. All these builds basically have problems with lock counter in particular. Instruments the VM in ways that completely change its performance, so you can't use it in production, right? This is basically true of all of these special builds. When you fire up the debug version of the thing, you also get something which is super useful. It's the emulator toolbox for pathologists. This is a large set of GDB scripts that actually allow you to introspect things in the VM. This is really helpful, not just for GDB. Like you can use the same logic that they use for decoding things like doing stack traces from system tap, for example. So it's actually extremely helpful. You can see, for example, in this case, I've got a NIF where I've set a breakpoint, and so when we hit that breakpoint, I'm able to print out the terms of the arguments to it, look at the process info. If I do ETP stack trace envproc, I would get the stack trace of that situation. So that that can be incredibly handy for some kinds of debugging. But like beyond that, something about ETP is just it's filled with a great condensation of information about how to introspect parts of the system. So the other thing, if you're writing system tap probes, or for example, I'm experimenting with some kind of crazy stuff involving perf counters that needs to read snapshots of the VM memory and do things with it. And the easiest way to figure out how to do that and how to do that introspection is actually just looking at the ETP script, which is this monstrous GDB script that actually partially gets generated in the build process. But it's still it's incredibly helpful, and it's filled with. I don't have the snapshot of ETP help here, but it's worth firing up just because there's a ton of commands, and you can see processes that are running, stack traces, all kinds of stuff. And it knows how to print terms, which is really handy. But ultimately, so there are a lot of places that you can't use a custom VM. Continuous integration. So, for example, we do a lot of builds on Travis CI, and things are slow enough without me building 20 different variations of the the VM at the same time. And I think it would be very inconvenient to do that. Also, the invocation of these things is inconvenient. Like, as far as I know, and maybe someone can correct me if I'm wrong, but it's really not trivial to get rebar to invoke, like, say, rebar shell or whatever, using the CRL, the debug CRL, for example, or similar. So this is just things that are inconvenient about those tools. So AFL fuzz, American Fuzzy Lop, is a great fuzzing tool. Incredibly powerful fuzzing tool that kind of not unlike what Costas showed yesterday. Like, it's kind of a reduced form of concurrent testing. It doesn't use an SMT solver, but it does instrument branches and do coverage-directed fuzzing. It's not really possible to use it with use it on the VM, for example. I know someone just recently I saw on IRC, somebody is actually working on using Clang's libfuzzer on OTP, which is awesome, but I mean, I think it's a mammoth undertaking. And finally, like production, that's the most important thing. You can't use this for diagnosing, you can't use any of these things for diagnosing faults in production, really. All of them, even I'm pretty sure the Valgrind build, introduce enough overhead if you're already pushing your machines really hard that they're not really practical. In response to that, especially because I had a lot of problems with NIFs, I had an idea, which is, why don't we implement just enough of the NIF API that we can load a NIF outside of the VM, right, and run things with it, so that we can run things under Valgrind and under GDB and fuzz them and so on. So I implemented a little harness called NIFy that basically, so it loads a NIF or multiple NIFs. You can supply several SOs on the command line. You can see there that it's loading Jiffy. It prints out what functions are defined in their arity. And then you can actually, you feed it Erlang terms, and it binds variables, and you can get the output. And the output is formatted as Erlang terms. Part of the reason for this is so that we can integrate it really well with like our existing test environment, and especially tools like Proper and other things like that, because you can just really quickly generate examples, pump them out to it with IO format or similar, and read them back in. And so that's really handy. And I'll go through a couple of cases where I've applied that and some other things. So one of the NIFs that I use is used for looking up IP addresses and net masks in like out of many lists of IP addresses, and it like has to build an index and does queries. And so there were a lot of changes happening to this NIF, and we wanted to really make sure that it was correct. This was actually one of the inspirations for writing the harness, because we had some really fun bugs. Like, I think my favorite war story from this NIF was that it would, at one point, it would crash when built with Clang, and it would work fine when built with GCC. And that's the kind of thing that's spooky enough that you don't like, but and that ended up being quite interesting, because it turned out, well, obviously it was a mistake in the code, but Clang ended up allocating quite a lot of things on the stack, and GCC elided the allocation. And just as a random word of warning, the stack that the NIF has available to it is quite limited. I think the default stack the VM gives you is something like maybe a maximum of 8 megs. Anyway, which is plenty for many things, but if you actually are, especially if you have C++ code that does a lot of allocate large things on the stack, it's very easy to blow it. So that's worth knowing. But so we wanted some ways to maybe ensure that this was actually correct. Especially I wanted to run it under Valgrind and check for memory leaks and things like this. So this is an example of, from the NIFy test suite, of a leaky NIF, and what Valgrind will report. So one thing about NIFy is, like, obviously there's no garbage collector, but what it does is it just keeps track of every allocation you made, right? It's not intended for long runs of your NIF. It's just, but every allocation is tracked so that basically at the end, we can easily sort of free everything that would have been accountable to the garbage collector. And so in this case, we were able to, at the end, detect that this NIF called enif alloc and didn't use an appropriate like enif make call afterwards to track it.
Can you actually allocate memory and then keep state and that survives in independent calls?
Yeah, in a NIF? Yeah, for sure. And in fact, many NIFs do that. right? And so in NIFI too, obviously, it keeps track of the environment, just like the same thing in both cases in the VM and in NIFI. Each NIF has associated with it an environment that actually all the allocation basically happens sort of within that environment, and there's a bunch of things, like usually there's a process associated with that environment. Although you can create new environments, there's a bunch of things around that, but basically there are a lot of ways to, if you do end up doing allocation in your NIF, there are a lot of ways to shoot yourself in the foot. So it's definitely possible to leak memory. So running your NIF under NIFI is one way to potentially detect those things. So you can use Valgrind to do that, or ASAN, the address sanitizer. One thing that's nice is you can build everything with -f sanitize address, -f sanitize, I think I discussed this, yeah. -f sanitize equals undefined behavior. These are really handy. One thing that turned up was a case where we actually shifted something, did I think a left shift by more than the machine word size. And of course, this is undefined behavior. So you have to be super careful about that, because one day your compiler may decide to shoot you for using this, for not masking your shift. And and it's certainly usually the unexpected, some unexpected behavior occurs. So that was one thing that we discovered by building with UBSAN. But so it's something that, I apologize for the duplication there. This is something that we do right now, is just generate random cases and run it under Valgrind. This is actually really handy for, especially when making changes, because you very quickly detect bugs that I just find are quite difficult to detect just running a normal unit test suite. And so one of the other things that we do for this, so you can actually use Erlang's tracing facilities on your test suite, and just send everything that your test suite is sending to the NIF in the VM, you can send to NIFI. So here we spawn NIFI under Valgrind as a port, and then we trace all the calls to the NIF module, and then we just have a little loop where every time we get a call, we send it to NIFI. And this is actually super handy, because then you just spawn this, and then you run your test suite or whatever else, and just all the calls get passed on. And then if it crashes, well, you get tons of ugly Valgrind output, but it's super useful for detecting. Well, I'll talk about that in a second. And also American Fuzzy Lop. So the other thing, to use American Fuzzy Lop, you have to build everything with AFL GCC or AFL G++. So that's one of the reasons it's quite difficult to actually get the VM to build properly and then AFL fuzz to run on it. And even then, it's not very practical, because it creates a ton of branch points. So in this case, you just have to build NIFI and the NIF itself. And you can just set the environment variables to point to AFL GCC and invoke rebar compile, and it'll do the right thing. Or if you're using rebar 3, you may have to tweak your make file. But after that, you can run American Fuzzy Lop on the NIF, and it's quite handy. So in this case, there's nothing. It was only running for 35 seconds. This is another case which is interesting. It's like 57 unique crashes after 23 seconds. You usually, the number of crashes is the number of unique crashes flattens out pretty quickly most of the time. But this is actually really nice for finding, especially anything where you might be, if you have any kind of NIF that there's any path for unsanitized input going through it. If you're doing just base64 decoding, JSON encoding and decoding, all sorts of things like this, I think it's really worthwhile actually fuzzing and using an intelligent fuzzing tool like American Fuzzy Lop. Just because it's much more effective than, trying trying to come up with your own fuzzing tools or trying to do this purely through property testing. So another case, finding an elusive bug. So this is something you never want to see, right? Performing eUnit tests, segmentation fault. Yeah, when your eUnit test seg fault, that's really not good. And so this was something this was what drove finishing, actually getting a working version of NIFy, because I really wanted to track down this bug. Because occasionally, it's with segfault and the unit tests for one of our systems, and trying to reproduce it, you open up like, for example, you set the you unset the core limit so a core file is generated, and you pull it open, and it's really not clear what's happening. Especially, basically, the crash is happening. Like, it appears that the crash is happening way after whenever the damage is done. And I mean, that's classic in C, right? Usually there's actually some corruption that occurs, and that's why Valgrind is great, because it detects that corruption at the time it happens. And it's often much later when the segmentation fault actually happens. It's like the damage is long since done, and it's hard to trace back to it. So this is what this crash looked like in GDB, just on the runtime. And then under Valgrind, it was much better. Valgrind reported it was an invalid read. It turned out that it was actually a race condition that if the tests ran fast enough, basically I won't go into it, but this NIF, loads other dynamic objects that have been compiled on the fly, and it turned out that it was using timestamps to differentiate the file names, and of course there was possibility of collision, and then there were certain cases where it didn't check some bounds. But anyway, this is great because this sort of definitively finds where that is and where bound checks need to be added. And so the third case is profiling and measuring performance things, benchmarking. So like in this case, I'll talk a bit about Jiffy and JSON encoders in general. One thing that I think I have a slide for this. Yeah. So like one thing I noticed for some workloads that we had, like basically the 99th percentile for pretty much all of the NIF-based JSON encoders was great. It was fine, but the variance with lots of workers was awful. Yeah, and just basically occasionally you'd have these real, like really brutal variants. And so just in the process of trying to rule that out, there were a bunch of techniques that you can use. So one of the things that we speculated about, because of the fact that the variance increases as the workers increase, so that tail measurement is really bad, right? So this is an awful hack. This is a terrible hack, but it actually works really well for quickly figuring out, identifying calls that were potentially too slow. And I'll note you can also do this with system tap, and I have also done it with system tap, but it's extremely persnickety to actually get exactly the right system tap invocation and get everything on your system set up to do it with system tap, whereas this is really easy. You drop this into a header file, right, and it basically just wraps all of the NIF API, and you build your NIF, and in this case, like I'm doing RDTSC, I'm reading the timestamp counter of the processor. That's a terrible idea because, of course, there could be a CPU migration, and then the value would be meaningless and so on. But in practice, it was enough. This is simple, and it's simple enough to pick up on really egregiously long API calls. So this actually doesn't run in NIFy. This runs in the VM. You build the NIF this way. You run your benchmark in the VM, and do I say it? No. But basically, so then it outputs whatever call was too slow and how long it thought it took. And that very quickly showed us that, like in this case, NIF realloc was occasionally really, really slow. And it turns out that, I mentioned it before, but when you're reallocating binaries, ref counted binaries, they actually get allocated by the libc malloc, and there can be really terrible contention between threads. So this was a way to catch that, and it's occasionally handy for catching other things like that, other performance outliers. The other thing that's really useful here is cache grind is one of the Valgrind tools. Actually, there's a lot of those tools are quite useful, but so with cache grind, we get kind of very predictable count of like how many instructions executed and a lot of things like that. And there's actually much more information we can get from it, but this alone is really useful for especially for comparing different implementations and just seeing, like with the same input, are they, sort of what is the instruction count? And sort of as justification for that, as a way of working, I want to cite one of my favorite quotes from hero of mine, Richard D. Hipp, who wrote SQLite and many other great things. He's talking about how they made a 50% performance improvement in SQLite over the course of a year. And that's SQLite as a very mature product already. And he says, like each micro optimization might improve the performance by as little as 0.05%. If we get one that improves the performance by 0.25%, that's considered a huge win. Each of these optimizations is unmeasurable on a real-world system. We have to use cache grind to get repeatable runtimes. But if you do enough of them, they add up. And that's one of the reasons I would say it's actually very handy to be able to cache grind your NIFs, especially when you're trying to really squeeze everything out of them. So NIFI is available on GitHub. There's a lot of stuff that's not implemented. Maps aren't implemented. Sub-binaries aren't implemented, but that will probably be in soon. There's some timing stuff that's coming that allows you to, especially, so an interesting aspect of timing and performance measurement is sometimes for micro benchmarks, you want to exclude measurements where any interrupt happened whatsoever. So I actually have a branch where uses perf event open to keep track of basically all performance counter events that happened during the execution of one measurement, and just to discard measurements that happen if any context switch has happened, for example. So that's kind of a handy thing. And if you have a lot of NIFs, you might find this convenient. So feel free to contribute. And I want to thank my employer, AdGear, for giving me time to work on this. Thanks. Yeah, and questions, obviously, because I'm sure we have plenty of time.
Yeah, we have like 10.
Yeah, it's probably more than 10 minutes. I went through that faster than I thought. So please, any questions, any NIF problems you have?
How did you end up fixing the slow allocation?
What's that?
How did you end up fixing the slow allocation?
So it's not entirely fixed yet, but moving to JE malloc actually made a huge difference. And like I mentioned, luckily, it happens that LD preloading JE malloc works okay with OTP as it is, but yeah, that's still sketchy. And so ultimately, so what I'm actually doing, I'm working on a new JSON encoder that will be open source at some point. JSON encoder decoder that has quite a different approach to how it produces its output. That really tries hard to get an IO list that is as close to an IO vec as possible when things get written out, and tries to avoid doing lots of large binary reallocs, basically. So.
I assume you're using R18 right now?
Yeah.
Have you noticed a real improvement in the scheduler's problem? The scheduler used to have very big problems with NIFs. Have you noticed?
I think it's better, but I think the biggest thing is, of course, the availability, the less experimental availability of dirty schedulers, right? Which you don't get by default, but like definitely is much more helpful than, I mean, they've definitely tried to do some things. It does make a difference, but really, if your NIFs are running for more than 1 millisecond, I don't know, you've got enif consume time slice, which is helpful, but the dirty schedulers would definitely be the thing I would go to. That's other questions?
Yeah. What operations are you using NIFs for in particular? Like,
Too many things. Too many
because
things.
you said you were using a lot, and I'm using
Yeah.
outside grid to none. So
Right.
I'm wondering.
No, it's good. It's good. Like I mentioned, we have a very interesting indexing problem that requires some very creative compressed bitmap techniques, and that initially was a NIF that actually has been moved out to an external service, but yeah, that's one thing, and there's like all sorts of things that have to be really fast. Basically, like we have really tight latency requirements. Things like georadius queries and things like this all have to be like way faster than just the naive implementation in Erlang would be. Machine Zone mentioned atomic counters. That's definitely something that we're into as well. Which actually reminds me, like one alternative to sort of to NIFs that you can use is you can use one NIF like EMMap to access shared memory basically, but use that as fast communication with external processes that also read that also mmap that page, and that's still safer than having a NIF. It still avoids a lot of kinds of issues with that. What else? Yeah, lots of things. Base64, quoted URL decoding, JSON, tons of stuff.
Processing like JSON put above string like upper to lower.
Yeah, pretty much everything, anything that isn't I/O is in a certain sense like.
Anything that pops out when you do like a basic profile.
Yeah.
You're using like the built-in.
Another thing, I hopefully will have some interesting work on perf at some point that's related to this, ways of basically probabilistically sampling the system state, and especially what's happening in the VM from outside, instead of, I feel like any approach based on instrumenting it inside is really difficult to actually pull off in production, as pretty much anybody who's tried to trace in production has seen. Right? So hopefully that will come out at some point. Other questions? No? Okay, well, thanks.